Imagine a point of no return in the cosmos, a gravitational abyss so profound that not even light can escape its clutches. What would truly happen if you, or anything for that matter, dared to cross the event horizon of a black hole? Prepare for a journey into the most extreme environments in the universe, where the laws of physics as we know them are stretched, warped, and ultimately broken into questions that defy easy answers. Welcome to Orbital Arc, where we unravel the mysteries of the universe. Today we confront one of the most enigmatic objects known to science, the black hole. We're not just going to define them, we're going to dive headfirst into the black hole paradox, exploring the mind-bending consequences of crossing its threshold. From the gruesome phenomenon of spaghettification to the perplexing implications of the information paradox and the hypothetical firewall, pushing the boundaries of what we understand about reality itself. Before we can contemplate the terrifying journey into a black hole, we must first understand what these cosmic behemoths actually are. A black hole isn't an empty void, but rather a region of space-time where gravity is so intense that nothing, not even light, can escape. It's born from the collapse of massive stars, crushing their immense mass into an infinitely dense point called a singularity. Surrounding this singularity is the event horizon, the infamous point of no return. This isn't a physical barrier, but a boundary in space-time. Once you pass it, the escape velocity required to leave exceeds the speed of light itself, making retreat utterly impossible. There are primarily two types: stellar mass black holes, formed from the remnants of massive stars after supernova explosions, and supermassive black holes, millions to billions of times the sun's mass, found at the centers of most galaxies, whose origins are still a topic of intense research. So let's set the scene. You're an intrepid astronaut piloting your vessel closer and closer to a supermassive black hole. As you approach, you wouldn't feel anything unusual at the event horizon itself. It's not a shimmering wall or a sudden jolt. In fact, for a supermassive black hole, whose event horizon is millions of kilometers across, you might not even notice you've crossed it until it's far too late. The light from distant stars would appear distorted, stretched, and warped around you due to the intense gravitational lensing, creating bizarre visual effects like multiple images of a single star or even entire galaxies appearing as distorted arcs known as Einstein rings. From an outside observer's perspective, however, your descent would be agonizingly slow. They would see your spaceship appear to slow down, become increasingly redshifted, and eventually freeze at the event horizon, its light fading into oblivion as time itself seems to grind to a halt for you, a phenomenon known as infinite time dilation. But what happens once you've truly crossed that invisible line? If you're falling into a stellar mass black hole, which might only be tens of kilometers wide, your fate would be gruesome. This is where spaghettification comes into play. The gravitational pull on your feet, being closer to the singularity, would be exponentially stronger than the pull on your head. This difference in gravitational force, known as tidal force, would stretch your body like a piece of spaghetti, tearing you apart atom by atom long before you reach the singularity. Imagine being stretched lengthwise while simultaneously being compressed laterally, like toothpaste being squeezed from a tube, until you're a long, thin stream of subatomic particles, utterly unrecognizable. For a supermassive black hole, these tidal forces are much weaker at the event horizon due to the larger radius, meaning you might cross it intact, only to face spaghettification closer to the singularity, deeper within its gravitational well. As you plummet deeper, relativistic effects become increasingly pronounced. From your perspective inside, time would continue normally. You wouldn't perceive yourself slowing down. However, the universe outside would be playing on fast forward. Billions of years could pass in the outside universe in what feels like mere moments to you. The light from behind you, that is, light from the universe you just left, would be blue shifted to extreme energies, potentially blinding or even incinerating you with its intensity as those photons gain immense energy falling towards you. Within the event horizon, all paths in space-time lead inexorably inward. Forward in time literally means towards the singularity. There's no escaping, no turning back, no matter how powerful your engines. Ahead, you would see nothing but the increasing darkness of the singularity, a point of infinite density and zero volume, where all known laws of physics cease to apply and our current understanding breaks down. Once spaghettified, or simply once you've passed the point of being stretched into a stream of particles, your journey inevitably leads to the singularity. Here, our understanding of physics completely breaks down. General relativity predicts a point of infinite density where all the mass of the black hole is concentrated. But this is a mathematical idealization, a sign that general relativity is incomplete without a theory of quantum gravity. What happens to the information that made up your body? The no-hair theorem suggests that once inside, a black hole is characterized only by its mass, charge, and angular momentum, implying that all other information about what fell in, its shape, composition, history, is lost forever. Physicists often describe this as a black hole having no hair, meaning no distinguishing features beyond these three fundamental properties. This leads us to one of the most profound conundrums in modern physics, the black hole information paradox. The information paradox pits two fundamental principles against each other. General relativity, which states that information should be lost within a black hole, and quantum mechanics, specifically the principle of unitarity, which dictates that information can never truly be destroyed, only transform. Stephen Hawking's groundbreaking work on Hawking radiation proposed that black holes aren't entirely black. They slowly evaporate over eons by emitting thermal radiation. He theorized that virtual particle-antiparticle pairs constantly pop in and out of existence near the event horizon. Sometimes one particle falls into the black hole, carrying negative energy, while its partner escapes to infinity, carrying positive energy. This effectively causes the black hole to lose mass and radiate. However, if this radiation is purely thermal, it carries no information about what fell into the black hole, thus suggesting that information is indeed lost. This created a profound crisis in physics. If information is lost, it violates the fundamental principles of quantum mechanics, challenging our understanding of the universe at its most basic level, where every process must theoretically be reversible. This paradox led to the radical firewall paradox. If information must be preserved, some physicists propose that a firewall of high-energy particles might exist at the event horizon. This concept was dramatically highlighted by the AMPS collaboration in 2012. Their argument suggested that if Hawking radiation is entangled with the black hole's interior and also with particles that escaped earlier, it violates the principle of monogamy of entanglement, a quantum rule stating that a particle cannot be maximally entangled with two separate systems simultaneously. To resolve this, they posited a violent disruption at the event horizon, a firewall. However, such a firewall would violate Einstein's equivalence principle, a cornerstone of general relativity, which states that an observer falling into a black hole should experience nothing unusual at the event horizon. It should be just like passing through empty space. The existence of a firewall would create an absolute distinction between a free-falling observer and a stationary one, a distinction that relativity forbids. This creates a deeply unsettling conflict between quantum mechanics and general relativity, two of our most successful physical theories. The search for a resolution to the firewall paradox continues to drive theoretical physics. Some theories suggest that the event horizon isn't a sharp boundary, but a fuzzy region, or that information is encoded in subtle quantum correlations within Hawking radiation in a way we haven't yet fully grasped. Other, more speculative proposals include the holographic principle, which suggests that all the information about a black hole's interior is encoded on its 2D surface, much like a hologram, meaning information isn't lost but merely projected. The fuzzball theory posits that black holes aren't singularities, but instead are diffuse, quantum objects made of vibrating strings with no true singularity or empty space inside. More radically, some speculate about black holes being gateways to other universes or baby universes, though these remain highly theoretical. The truth is, we don't yet have a definitive answer. What we do know is that black holes are not just cosmic vacuum cleaners. They are laboratories where the universe tests the very limits of our understanding, pushing us to develop new theories that might reconcile the seemingly disparate worlds of gravity and quantum mechanics and ultimately lead us to a unified theory of everything. Our journey into the heart of a black hole, exploring the terror of spaghettification and the mind-bending information and firewall paradoxes, reveals just how much we still have to learn about the universe's most extreme phenomena. Black holes remain one of the most active frontiers in physics, challenging our core assumptions about reality, time, and the very fabric of space-time itself. The quest to understand them is a quest to understand the fundamental laws governing our existence. What do you think happens to the information? Could black holes be more than just destroyers of matter, perhaps cosmic information processors, or even creators of new universes? Let us know your thoughts in the comments below. If you found this cosmic dive as fascinating as we did, make sure to like this video, subscribe to Orbital Arc for more deep dives into the universe's greatest mysteries, and hit that notification bell so you don't miss our next adventure. Until then, keep looking up and keep questioning everything.